In the last video, we looked at the basics of Rapidity, such as how to create new projects and how to change basic configuration settings. This time, we'll be looking into basic debugging techniques, including simulation and how to view our peripherals while running a program. To make life more interesting, this time we're going to be using an Ada example project. If you remember from the C example project, there were two configuration files, config.h, which stores all the basic configuration options, and config.c, which stores the task specification. In Ada, all of this information is stored in a single file, named config.ads. If we look at it, we can see we have our oscillator frequency, our tick period, and our logging settings, just as we did in C. In addition, we have the task array containing the specification of all tasks. This is in exactly the same format as the C file, as we can see if I drag the view over and we can view them side by side. So we can see that Ada, just like C, has the task function, the period, the delay, the worst case execution time estimate, and the recovery task, just as the C tasks did. In Ada, just like with C, if I want to go straight to the definition of a task, I can simply hold down Control and click on the name. This will take us directly to the source code for the task itself. In fact, I can do this with any function. Simply hold down Control, click on the name of the function to be taken directly to its definition. Just as with C, we have a project settings file for Ada. It contains all the same items that we had in the C version. In exactly the same way, if I click on one of the links for the configuration items, it will take me straight back to the relevant area in the configuration screen. So now let's try some debugging. From the project settings page, simply select Simulate and Start Debugging. As you can see, we're now asked if we wish to switch to the debug perspective. The debug perspective, much like the Rapidity perspective, is a collection of views that's dedicated to one specific task, in this case debugging. Clicking Yes will take me to the debug perspective. As you can see, we can get back to the Rapidity perspective at any time from the perspective buttons at the top right. Notice that execution has paused in the beginning of the main procedure. This is indicated by the green background to the line and the arrow to the left. At the top, we have the debug view. This shows us the current function and the stack trace of any other functions that called it for the current time. Above this, we have the debug controls. This allows us to resume, pause, terminate, disconnect, step into a function, step over a function, and step out of a function. It also allows us to do instruction stepping, which involves stepping over individual assembly language instructions. Let's try stepping into the current function to see what happens. As you can see, we're now in the scheduler init function. At any time, we can look through the stack trace to see the function that called this current one. You might also notice at the top right the variables view, which is showing us all current local variables, in this case the tick micro variable. Now let's get back to the main function by stepping out of scheduler init. We can set a breakpoint by double clicking in the margin of the editor window. A breakpoint has now been set on the scheduler dispatch call. If I select resume from the debug view, execution will resume until it reaches the scheduler dispatch call, at which point it's now paused again. I can remove the breakpoint again by double clicking once more. Breakpoints can also be edited or removed from the breakpoints view, as you might expect. Finally, we have the peripherals view, which gives us access to all current peripherals in the process. In order to fill this view, we may have to perform a single step operation. We can now see the peripherals. You may have to resize this view to get a better view of what's inside. As you can see, we have access to all the information about our timer peripherals, including our registers such as control and our prescaler registers, as well as utilities to show us how the timer is currently set. Next, we have our GPIO peripherals. In this particular example, GPIO1 is a Knight Rider style pattern from bit 0 to bit 17. These flags indicate the direction of those pins. The flags above indicate the current value, showing that a low signal is currently present. If we click resume, we should see a 1 value moving along. Next, let's look at some of the other peripherals. This example uses UART0 to output a basic menu. If we click, we can enter our own values. Let's resume once again and try entering a value. Finally, we have a 7-segment display example. If we resume once again, we can see that this is counting up continuously. That's it for this video. Next time we'll be looking at our timing analysis functionality and how to see that the simulator itself is accurate right down to the cycle level. Thank you for listening.